So let's continue, right? So we were talking about dynamics, right? We said dynamics basically includes kinematics and kinetics. We said kinematics. Well, we talked about it for first 3-4 weeks. Depending on what coordinate system you consider, you just study position, velocity, and acceleration. In this case, we're mainly focused on acceleration. We still care about what we learned about velocity and position, because once you know acceleration, and that's why when we were talking about acceleration, we were so focused on acceleration. We classified the motions based on acceleration. We said the motion acceleration can be a function of time, velocity, position, or it can be constant, right? And that's why we were so focused on acceleration, because acceleration is the part or is the component that links kinematics to kinetics and basically forms the whole dynamics, the topic that we are covering in this course. So once you know acceleration, right, from there you can go back to whatever we learned at the beginning and find out what the velocity is, what the position of the particle or object is at any given moment. Now, remember, this dynamics, we are interested in studying conditions of a particle, of an object. Right now, we talked about studying or looking into dynamics of an object using Cartesian coordinates. And what I'm going to do today is we're going to do the same thing, but this time we are going to use tangent normal or tangential normal coordinate system. So I'm going to put it under 2. Hopefully I'm using the right color. I think I refer to that as tangent. Tangent or tangential doesn't matter. Tangential normal coordinates. Pretty straightforward. The story is the same, right? If we have, let's say I have my coordinate system like this one, and let's put it this way. And then let's say this is X, this is Y. Then you have some particle, some path of motion. Think about it this way. So tangent normal, right? If at this specific point I'm looking at a particle, then would be this would be tangent, and normal we said is always the concave direction. So this would be EN. So the story is the same. Only thing changes is that the coordinate system. So I still say summation of forces, like Newton's second law. I apply that because the summation of forces, assuming that they are not zero, meaning that we have a non-zero net force, and that non-zero net force is giving some acceleration to our object or a particle or whatever that non-zero net force is applied to, right? So summation of forces is going to be MA. Force is a vector, acceleration is a vector. Since we are in tangent normal coordinate system, now we're going to see two components. Instead of seeing X, Y, Z, now we're going to see tangent components and normal components. So summation of forces in tangent direction is equal to MAT, and summation of forces in normal direction is MAN. And we know, well, there's nothing new there. The only thing that changes is the coordinate system and the way we decompose the vectors to find the components in these two directions. So AT and AN, you remember when we were talking about acceleration, we're talking about tangential normal coordinate system. We actually talk about that, right? We said tangent, let me write it just for review. Tangent component was derivative of velocity with respect to time. And normal components was component was v squared over rho, rho being the curvature, radius of the curvature. Right? So if you have that one, basically what you had at the top, it becomes summation of forces in tangent direction is m dv dt, and summation of forces in normal direction becomes m v squared over rho. Well, you just replace AT and AN to the equations. And we also looked at a special case. We said, well, if it's motion on a circular path, if you remember, we said for circular path, right? Basically, the AT and AN takes not a different form, but over there we know that the radius, we know the radius of the orbiter to say the radius of curvature is r, right, in a circle. So we said AT, we actually derived these equations, is r alpha, r being the radius of the circle, alpha being the angular acceleration, and we also said an becomes v squared over r. And if you replace these components, again, we derive these equations. I'll just give you the final value is r, or final expression, r omega squared. So you can, in a circular path, you can just plug this in and you still get summation of forces in tangential direction would be m r alpha, and summation of forces in normal direction would be m r omega squared. The left side is whatever we get from free body diagram. The right side is whatever we get from kinetic diagram. Remember, we said kinetic diagram, or a diagram that shows the inertial forces, is basically is the same. We draw the object and we put the components of acceleration, right, in this case tangent normal components, and just multiply that by the mass. That gives us the values of for the right side of this set of equations. That's pretty much all into it. Right, so we're going to look at a couple of examples, and hopefully these examples are going to give you a better sense of what the story is and how are we going to apply this. All right, let's just start with first example. Let me just wait on this if someone is taking note. I don't want to go fast. All right, hopefully it makes sense. Same story as Cartesian coordinates. The only thing that we changed was now we're going from Cartesian XY coordinate to tangent normal coordinate. All right, let's look at this example, the first one. Dynamics, you only get comfortable with it by doing examples. More the better. So let's have to draw a circle. So I'm going to do my best to draw a circle. This tool I have here doesn't really have a circle tool. Hopefully it does. There you go. So we have a disk, and let me draw this as good as I can. We have a disk. This is the center of this disk, called point B. There is a slot. This is a slot on the disk, and inside this slot there is this mass M. Let's call it mass A, connected to this center B using a thread or a wire or rod. Don't think about it as a rod. Think about it as a thread or a wire. Now this disk, one thing I have to mention, this is in horizontal plane. We are looking at this from the top, right? So I don't actually see myself here, so I don't know what this. All right, so we are looking at it from the top. So it's in horizontal place, and it's rotating. So rotating this way with some angular velocity, omega, and some angular acceleration, both of them counterclockwise. Right. So we have a mass inside this slot. There is a desk. There is a disk. We have this disk in horizontal plane. There is a slot on it. Right? Inside this slot, there is this mass M, and this mass M is held by a thread or a wire. Is attached to point B, or the center point B. So let me put it put the problem statement here. So we have a circular disk. Circular disk lies in the horizontal place. Horizontal plane. Why did they say place? Now, at this moment that we are looking at it, it rotates. It rotates with counterclockwise this direction, angular velocity. And that velocity is velocity of 4 radian per second. What else? And an angular acceleration and a counterclockwise angular acceleration and a counterclockwise angular acceleration of alpha is equal to 2 radian per second squared. Right. Now it's said that the 0.5 kilogram, so we're given the mass, slider A, right, the slider A is supported by the smooth slot. Smooth means no friction there, right? And the string attached. I can do this. Attached at B. Right. Now, what we are trying to find is we want to find the tension in the string and also the magnitude of the horizontal of the horizontal force exerted on the slide by the slot. Right. So, two things. Find. Thank you. Find the say tension in the string and the magnitude of the let's say horizontal force exerted on the slider. So we have to give some on the slider by the slot. I intentionally write usually the full problem statement because what I realize that a lot of mistakes happen when you go from problem statement to formulating the problem. Once you get that, usually most of you do the rest correctly. So here's the problem statement, right? Now, what I'll do is that, well, obviously we're in dynamics, so I have to find the part that I want to draw the free body diagram for. Now I have along with my free body diagram, I have to find out my kinetic diagram and form together or form the equation of motion using Newton's second law. Just basically that summation of forces is equal to 0. I have to put that together. Now I'm going to look at this slider, the block. that is sliding inside that slot. All right, I'm going to draw it here. All right, let's draw this here. I'm going to make it a little bigger, obviously, so we can see is equal to, whatever is free body diagram is equal to kinetic diagram. All right. Now here, this is a motion. Let's look at it this way. This is a motion. This A, if you think about it, when your disk rotates, this slider A, think about how it rotates, right? The disk is rotating. Slider A is inside the slot, so it means that it rotates with the disk, with this disk. As a result, that is slider A, and AB is just a thread, a fixed length. So as a result of that, A is going around on a circular path. Hopefully everyone see that. So since it's going on a circular path, I can use tangent normal coordinate system. You will see later on you can even use polar coordinate system. For in this case, let's just use tangent normal or normal tangential, whatever you want to refer to it. So I'll take this and this. Remember, tangent is in the direction of the motion positive, right? So I take this as AT. Normal from the point concave. Right? If you think about your curve, and this is the concave, this is going to be the direction of the normal. Part of it, that was your quiz as well. I want to make sure that you guys are comfortable with finding the direction of AT and AN. AT is the direction of the motion. AN is the direction, or let's just use we don't use AT and AN, ET and EN. Right? We represent these with. So that would be ET. That would be EN. All right. So this is my coordinate system. If you want to put it on this object, this slider, you can put it here, ET, EN. Now looking at the slider, slider A, I have, I'm isolating this, right? I'm drawing free body diagram for this. So you can think about this being isolated there. And we are trying to draw the free body diagram for this. Forces. Well, I have one force that is the thread or the wire AB. I cut through. So it's always, remember, ropes, wires, cables, chains, they're always in tension, you know, forces. Now, if there is a cable under compression, you can eliminate that from the problem, as if it doesn't exist. Call that T. Yes, so we're taking it as point A, looking at slider A. We're drawing a free body diagram for that. And the reason is we have a lot of information about it. I know its mass, and I know it's rotating with the disk, so I know its angular velocity and angular acceleration. There is nothing else we have that much information about. Now, since it's, let's see if you can see this. Since it's rotating, and remember it's in horizontal plane. I'm just doing this because the camera is here. Since it's rotating, slider A is in contact with the slot there at the bottom, right? Or at this part. Here is what I'm trying to say. I'm saying this is the contact point. This is the contact point right here. If it was rotating the other way, the contact point was at the top. Or again, in horizontal place, it's hard to refer to it. But now that it's rotating counterclockwise and the acceleration is counterclockwise, obviously for the disk to carry slider A with it, right, the contact should be at the bottom. Right? Slider A should be in contact with the disk at the bottom, the red area I can draw. So I'm going to put the normal smooth contact or normal force right there. And again, if the rotation, the acceleration was the other way around, would have been a different story. Any other force here I'm missing? Or no, that's all we got. mg, that's what I wanted you guys to mention, so I can say it's a little bit of joy of being a teacher, I guess, to say no, it's wrong. Well, one thing I've been trying to mention is that we are in horizontal plane, right? So there is mg, you are actually right in a sense, but in our free body diagram, we don't really, it doesn't come into play in tangent normal coordinate system. There is an mg, if you want to put mg there, you can in one way, I guess, somehow, but mg is going to be inward to the screen. Since this is a top view and we have our disk on in horizontal plane, you have your, so we have tangent this direction, normal in this direction, tangent in this direction, normal in this direction if it's rotating, and you have your mg downward. Now, in a sense, you're right, there is an mg, but that doesn't really come into play in the way we are looking at this. So I do not put it here, but keep in mind that mg is inward, right, to the screen, because we are looking from the top. Hopefully it makes sense. If it doesn't, stop me. So again, I'm eliminating mg, but not because it doesn't exist, because it just because it's not really, it doesn't matter. You can, and any way you want to show, you can just show mg as going inside the screen. If you really want to show that, you can put it like this as mg. Actually, it's going inside the screen, so it's going to be like this. I won't show it because this gets messy and then things get lost. But remember that it is there, just in a different direction. Now, this is our free body diagram. Now, in kinetic diagram, well, I have AN and AT. I'll just put it there. I'll figure it out later. I always put it in the direction of the components of these axes. So that would be MAT, and that would be MAN. Because this is AET, this is the direction of tangent, this is the direction of north. Once we establish this, the rest is pretty straightforward, hopefully. Right? Summation of forces is equal to MA, is equal to MA. Since we are in normal tangential component coordinate, summation of forces in tangent direction is equal to MA tangent, and summation of forces in normal direction is equal to MA normal. A tangent, let's see if you remember that this is a circular motion, right? This, by the end, basically this slider is rotating or moving on a circular path. So that will give me AT as R alpha and AN as R omega squared. This is what I was just talking about here, right, right there for circular path. You have your AT here, you have your AN there, or better to say here what I'm talking about. So R alpha would be, I haven't given you R, so you would be probably yelling at me right now, saying, where is R? R is this distance is actually given in the problem. It's 0.6 meters, so there is nothing really hidden there. It's just I forgot to put it there. So R is 0.6. I don't know why it's so suddenly. So R is 0.6. I can get it right. Times alpha is 2. So that would be 1.2 meter per second squared. 0.6 times omega, this is alpha, omega is given also somewhere here, angular velocity 4. So that would be 4 squared. 16 of, I don't know, I have to look at my number. That becomes 9.6. 9.6 meter per second squared. So once we have that, there you go. It's pretty straightforward, right? The first one becomes, let me write it here. T, remember, you're writing in tangent normal coordinate system. So your normal, your tangent would be n, looking, and it's in positive direction. Your tangent is positive upward. Look at the coordinate system we put here. Right? Don't get confused about positive and negative, please. So tangent is upward, your n is upward, so it's positive, is equal to MAT. Well, it's also, we put it upward. AT and MAN, we always put it in positive direction. MAT, well, it's M. AT, I got 1.2, so I can just write it as, and the mass is 0.5. So this becomes 0.5 times 1.2. M or alpha. I can write it as, just later on, if you guys make sure that you follow what we did here. It becomes M or alpha. M is 0.5 kilograms, alpha is 1.2. We calculated that. In normal direction, T is to the left, so it's positive, is equal to kinetic diagram MAN, which would be M R omega squared. We calculate that. M is given as 0.5 kilogram, R omega squared is 9.6. Right. From there, you actually get your N and T. These are two things that they were asked. So you get N as 0.5 times 0.5, 0.2. I guess it becomes 0.6. Not wrong. It's Newton. And that'll be 0.5 times 9.6. I don't know. Becomes 4.8. Yeah, thank you, Sam. 4.8 newtons. There you go. So these are what we were looking for. All right, the solution, the final answer. We're looking for the tension in the string and the magnitude of the horizontal force. All right, question on this one. So if there is no question, let's look at the same problem, a little bit of different geometry. All right, so for next example, let's say we have the same geometry. I'm going to try to draw, see if this tool works. I have a horizontal plane. Now, this time, I have the slot in this way. Story is the same, or just now I have this in this direction. Call this A, or at least I try to A. This one is, this is point B, and now the thread is attached to a point here. Let's call this, okay, let's call this point B instead. And not call this anything, I guess. And this is also the, that's horrible. Let me see if I can draw a better vertical one. So this is 0.6, and this is also 0.6 million. Can think about this point of. This is 90 degrees right there. So I'll just write it this way: the same geometry, but omega, and this is alpha. Omega is the same also, 4 radian per second. Alpha is, so it's given this way. Omega is 4 radian per second constant, or let's be a little, and constant. MA is 0.5 kilogram, the same as before. Now we want to find tension in the string AB, and force exerted on slider, on the slider, slider A. So still horizontal plane. The only thing that changed is that instead of having that slot in like a line with, let's say, the radial direction, now I have it, it's some angle. I tilted. Still omega. I did not have any plan to. So this is still omega. This is alpha. All right, so let's draw the free body diagram again. Same story. I'm going to isolate this. That's the part that I have most of the information about. There is really nothing else you can draw the free body diagram for, or at least from what I see. Let's draw it the way it is. This is going to be the free body diagram is equal to my kinetic diagram. Now, this is still the motion, right? This is when it rotates in horizontal plane, you will still have the same. If you follow slider A, it still moves on a circular path. So that circular path didn't change. AB is the cable. Since we're accelerating this way counterclockwise, again, in horizontal plane. AB is under tension. I think about when you, I guess the best thing I can think of this, think about is imagine that you use a wire or a cable and then attach some heavy object on one end and start rotating that around. Right? So because of that acceleration, centrifugal force, that we'll talk about it maybe later on when we get to rigid bodies, but pretty much the force applied because of this rotation, right? You're gonna have tension in your cable. Once you start rotating, once omega is gone, remember this acceleration, this normal acceleration you get is caused by r omega squared, right? This is the normal acceleration. Now, this is the acceleration that the object has that gives the object tendency to run away from the center of rotation, right? When you have a rope, you tie something at the end of it and start rotating that, or you start turning around while you're holding the cable or wire with something attached at the end, heavier the better. This r omega squared is what is keeping this cable under tension, because that object is trying to run away from the center, right? Because of this acceleration component, this component of acceleration, r omega squared. once you start turning around, or once you start, when you stop turning around, or you stop turning it right, around the center, omega becomes zero and there is no acceleration, so that cable is not going to be under tension. Just keep that in mind. That normal component is what is giving this acceleration to the object, so the rope stays under tension. It's a little bit of physics of the problem, but what I was trying to say is that this object A, this slider A, is still going on a circular path. I think about this disk, and AB is the cable under tension. So when it rotates with omega, you still have R omega squared pointing from where the slider is to the center of rotation, right, along EN. So the story is still the same in terms of the way this slider is rotating, or the type of motion the slider is going through. It's still a circular motion, and you still have your tangent normal components, right? This is this, and this is this. This would be your ET. This would be your EN. I'm going to put it right here. This is ET. This is EN. Right? This is along the path. This is normal to the path, right? Pointing from where the slider is to the center, the concave direction. So don't get confused with this rotation, right? The rotation, we rotated this slot and the object, but the motion is still a circular motion. So ET and EN are still the same. Then the question would be, what changed then? If that's the same, it means we still have the same components on our object, right? On our kinetic diagram. We still have MAT and we still have MAN. So this is our kinetic diagram. Now the question would be, what changed? Well, for a start, T changes. Right? The tension force, because of this wire or string, I switch between wire, string, cable. I keep probably doing that throughout the course, but keep in mind, we're just talking about the same thing. String, cable, wire, they all behave the same in this course. So that would be your T. Right? Because it's along the cable. You're isolating that object or slider A, cutting through the cable. This is your T. One more thing changes, and that's the normal force. That changes too. Now, if you are rotating in this direction, let's they're going in this direction, right? This is the direction of rotation. So that would be the contact, right, surface that you have right there, because you're rotating this way. This slider is moving because of the motion of the disc. So there has to be a contact somewhere to push the slider with it. Since we are rotating in this direction, or looking from the top in this direction, the disc is pushing the slider from the bottom to move it with the same velocity. Right? That means I'm going to have my normal force here. Or let's see if I can do a better way. Oh yeah, that's good. Put it here. Normal force. So my coordinate system is the same. The components of acceleration, which basically form my kinetic diagram, whatever I have in kinetic diagram, are the same. Because of this rotation, now I have a different direction for my tension force and normal apply to this. So if you take this as horizontal direction, looking at this triangle right here, I can do better. Triangle there. Looking at this triangle right here. Someone tell me what is this, these angles? This is 0.6, this is 0.6, this is 90 degrees. So what is this angle or this angle? Exactly, 45. Thank you. They have the same size, like it has the same size, 0.6, 0.6, 90 degrees in the middle. So these are 45 degrees, 45 and 45. You don't know the angle, you can just find it by finding a tangent is equal to the opposite over adjacent. So tangent of 0.6 over 0.6 gives you tangent of 1. Tangent 1 is basically the tangent, 1 is the tangent for 45 degrees. You can use your calculator and find it. So this becomes here, this becomes 45 degrees, which means this is also 45 degrees. All right. So once we get this, the rest is not really, should not be a big problem. We just decompose the components in tangent normal and find what you're looking for. So summation of forces is equal to MA. Right? M and F and A are vectors. In this case, we are using tangential normal component coordinate system, which means summation of forces in tangent direction is M A tangent, and summation of forces in normal direction is M A normal. Same story. A tangent is R alpha. A normal is R omega squared. Right? That doesn't change. So what is AT? Can someone tell me what is the tangential component of the acceleration? That's something you have to pay attention to as well. It is 0, exactly, right? Because alpha is 0. We said here it's specifically said omega is 4 radian per second and constant, which means alpha, angular acceleration. Remember, angular acceleration was the derivative of time from angular velocity. So this becomes 0. Why? Because this is 0, omega is constant. R omega squared, what is R here? Well, I already draw it there, so you guys should be able to figure that out. Remember, R, don't get also confused with it. R is the distance from where the particle is or the object is to the center of rotation at that specific moment, the point that is rotating around it. So what is R? It is 0.6, exactly. Thank you. So it's 0.6, and omega is given as 4. So this becomes 4 squared. Let's just leave it like that. So tangential components of the force. Let's look at the tangent direction. We have T, and we are writing the left side of the equation of motion, like Newton's second law. Summation of forces in tangential direction. So on free body diagram, what do we have? We have, I'm playing around with colors here. Okay, so we have T sine 45 degrees, and it's in positive tangent direction. So this is T sine 45 degrees. And on the right side, we have, interesting. This problem is going in an interesting direction. Okay, so let's do that, see how things work out. And we have N plus N sine 45 degrees. On the right side, tangential component AT is 0, so this becomes 0. What does this tell me? Interesting. So I deduced, or I concluded, that normal force should be in this direction, right? The direction I put on this free body diagram, this normal force. I said it should be in this direction based on the direction of omega. Alpha is not given, so I just made that assumption because if it's going in this direction, I don't know if accelerating or decelerating or the constant acceleration, how is it affecting the normal force. Now, based on what they wrote here, this, right here, what do I get before even getting into the normal component and writing the equation for them? Exactly, Connor. But just I'm being moving around, just randomly going around or talking about this just to get to the point that you mentioned. N is in the opposite direction. Why? Because if you, from this equation, you will get n t equals to minus n. Now, if t is equal to minus n, t cannot be, well, the direction of the t I'm sure of, because t is under tension, right? The cable wire or string. We said wire cannot be under compression, so I can't change the direction of that. So this means that, or better to write it this way, n is equal to minus t, meaning that I have to switch or flip the direction of n is the only way that this free body diagram can work or make sense. So again, if I keep it that way, and we are writing it in tangential component though. You see that, not the normal component. Tangential component, this one is going upward as positive. So it is written in positive direction. So the only way that this works is that the n is in the opposite direction. Now you can do it. Exactly. So conceptually, the normal force is not, my conclusion was, my assumption was that, well, this is moving omega because alpha is not given. If you know the direction of alpha, that gives you a better sense of how things move. But since alpha is not given, right, alpha is the one that is forcing this constraint. Well, since alpha is not given, alpha is constant, omega is constant, so alpha is 0. It's hard to tell when there is no alpha which side this one is leaning to. Now, my assumption was similar to what we did before. I was like, well, alpha is 0, but if we had alpha, the contact would be on this side. Since we don't have any alpha, I'm just assuming that this is the direction of the contact because I'm assuming this is, let's say, the if we had alpha, would have been in this direction, and I made that assumption. Now, since alpha is 0, it can be any side. When I draw the free body diagram with my assumption, I realize that, well, it doesn't make sense. The only way that n could exist, which it does, is the opposite. So you have two options: either flip the direction of n on free body diagram right now and write it again, or continue solving the problem. But remember, wherever you have n, you have to put minus n. Right? Mathematically, you can still solve this. You just get a value for n as negative. You plug it in the second equation. You can find your normal tension, T. Mathematically, it doesn't really matter. You just have to remember that n should be in opposite direction. If you keep it in this direction, you get the negative value for n. So wherever you have to plug in n value for the rest of the problem, remember that you have to plug in the negative value. Or we can flip the direction right now and get a positive value for n and do this, solve the rest of the problem. Just going to pause a second to make sure that it made sense. So when you assume a direction, like free body diagram, similar to what we had in statics, if you're wrong about your direction, you're going to end up getting a negative value for something that shouldn't be negative. Right? In this case, your either n is negative or t is negative. So if you get the negative value for n, it means the direction you assumed was wrong. The magnitude is correct. You have two options. You either flip the direction of the force on your free body diagram and solve the problem again, or just continue solving the problem. Remember, whenever you're dealing with that force that you found negative value for, you have to plug in the negative value. Later on, let's say you have something based on n, you have from the second equation, you get 3n plus 5 is equal to something. Remember that plug in the negative value for n. For instance, if you got n as minus 10, remember to plug in minus 10. Just some random number. All right. So here's what I'm going to do. I'm just going to, since we figured it out soon, at the beginning, I'm just going to flip this. But again, remember, you can either flip it or you can just keep it the way it is and plug in the negative value. You get the same thing, same story. So this becomes, I'm going to do it this way, m. Hopefully everyone followed what I did there. Mathematically, again, you get the answer as long as you use the negative value for the rest of your solution. But physically, the physics of the problem tells me n is in the other side, because the negative value doesn't make sense, right? Oh. Well, it does, but shows the opposite direction. It shows that I assumed the wrong direction. So this becomes n. I think the only thing that changes here is minus. I don't know why they changed the color. So this becomes minus n sine 45 degrees. N sine, yeah. All right, so we resolve that. Going to the second part, summation of force in normal direction is equal to m-a-n. So en, well, I have t there. T is t cosine 45 degrees plus n cosine 45 degrees. Now that I took n downward, is equal to, go to kinetic diagram. En is this way. M-a-n is obviously always take it as positive, would be m r omega squared. M is given as 0.5, R is 0.6, and omega is 4. In this set of equations, you have two equations, two unknowns. You don't know what t is, you don't know what n is, and these are what you're supposed to find. So two equations, two unknowns. Mathematically, you can solve this. So from there, you'll get t as, maybe you can write, I'll just give you the answer. You should be comfortable with solving two equations, two unknowns. You can find n as a function of t from the first one, plug that into the second one, and solve it for n. Once you know n, you can just find t. Let me know if you have a problem with this one. From the first one, it's pretty straightforward. We get t is equal to n. In this case, because it's 45 degrees, even if you don't follow the process, you can get from the first one, t is equal to n. From the second one, you get, if you plug that in, you can get, you'll get actually t is equal to 3.39 newtons. So this is what you were looking for. All right. Question on this one. So I did make an assumption about the direction of n, which was wrong because I didn't know the acceleration, or acceleration is 0. If acceleration was counterclockwise, that assumption was right. But since it wasn't there and it was 0, it could go either side, either direction. All right. Another example. See if I can do 2 examples in 15 minutes to see how fast we go. Example. Now we have, this should be pretty straightforward, hopefully. We have mass m. This mass is attached to 2 supports with 2 cables. I'll say this is one support, this is one support, two walls. This is 45 degrees, this is M, this is cable A, this is cable B, and this is support. Now the problem statement says the suspended mass, the suspended 2 kilograms mass is stationary, meaning that's just standing there because of two cables. One is holding it this way, the other one is pulling it this way, the other one is pulling it this way. It's in static equilibrium. Part A is just from a statics, right? So nothing really complicated there. Part A tells you to find the tensions in cables and strings A and B. So find the tension forces in string A and B. So that's easy. It's just free body diagram again from statics. Nothing is moving. It's in a static equilibrium. So I have a mass, two tension forces there. I'll just draw it here. I have this one as one tension. I have this one as one tension, and I have weight downward. It's supposed to be this weight. I'm going to make it bigger. So this is M. This is TB. This one is TA, and this is mg. So that's not very complicated. You want to find the force. This is 45 degrees. Just find the summation of force in different directions, right? Direction X and Y, if you want to think about it that way. I'll just do it in a not clean way, but it's a statics. So I'm hoping that you guys follow. So it becomes TB sine 45 degrees is equal to mg, and TA is equal to TB cosine 45 degrees. These are two equations I get, one in X direction, one in Y direction. And from there, we can just find the values. From the first one, TB becomes mg over sine 45 degrees. And from the second one, once you know TB, you can find TA. All right, so TB cosine 45 degrees. TB from the first one, you will get 27.7 newtons. Once you know that, plug it back to the second one. TA is 27.7 cosine 45 degrees. That will give you 19.6 newtons. So part A is pretty straightforward, hopefully. If it's not, let me know. I'm just going with the assumption that it is, because it's stationary and nothing is moving. You only have free body diagram. No, nothing is accelerating. Now, part B is the interesting part. Is part B. It says if we cut string A, like string A and B are holding this. Now, I'm cutting the string A. Right? If string A is cut, I want to know what is the tension force in string B immediately after I cut A. This is an important phrase, immediately after. So if a string A is cut, what is a tension? And I can write a better tension there. What is the tension in string B? And the phrase is immediately after. Afterwards. So let me write it here. Afterwards. So immediately afterwards, the moment I cut A, well, A doesn't exist. Once you cut A, remember when we have the phrase immediately afterwards, meaning that especially, okay, let's think about this. When we have something that's in static equilibrium, and for some change in the system, it goes out of equilibrium, right? It's not in a static equilibrium anymore. If you cut cable A, obviously mg is going to pull this mass down. So it goes out of a static equilibrium. Now, when we say immediately after, meaning that immediately after the object or the particle or body is not in static equilibrium, it means we are saying that this change happened. So the object is going to have some acceleration. Like immediately after, the gravity is pulling it down. So it starts accelerating this mass. However, since it's immediately after, the acceleration doesn't have enough time to give velocity to the object. So I'm going to repeat. This is an important concept. Velocity, going back to position, velocity, acceleration. Velocity is caused by acceleration. You see in dynamics, we give something, we apply a force, that force causes acceleration, Newton's second law. And that acceleration, given enough time, gives the object velocity. When you give an acceleration to something, you need some time, right? A is dv dt, or v is equal to a dt. You can think about this. So you need some time, right, from 0 to 2 seconds to give some object velocity due to its acceleration. Now, when we say immediately after, meaning that you don't have that much time. Let's say it goes from 0 to 0 plus a fraction of a second. So there is not enough time for the object to gain velocity because of the given acceleration. Right? So here is that's the phrase there. That's what that phrase is trying to tell you. That when we say immediately after, think about it this way: we have acceleration, but we don't have velocity. Immediately after going out of a static equilibrium. So that's what happens here. When we say immediately after cutting this cable, so here is what we have as free body diagram. We have a still or tension in this cable, cable T, cable B, so call this TB. This is mass M. You will still have gravity pulling down. This is mg. This is 45 degrees. Now it's equal to kinetic diagram. Now, in your kinetic diagram, you have acceleration, right? What happens when you cut this cable right here? This mass starts moving in this direction. And you can think about this as a motion on a curvilinear path. You cut this, it just starts going down. Eventually, it becomes like a pendulum. It goes down all the way to the other side, comes back to this side, and it starts oscillating. But immediately after, you're going to get two acceleration components. Stop me if it doesn't make sense to you. We have, since it's a motion on a curvilinear path, now we can look at it as like this. E tangent, E normal. So object following a path, right? And that path is just a curvilinear path. So I'll draw it the way I see it, right? This tangent, and this is normal on my kinetic diagram. This becomes MA tangent, MA normal. And here is my tangent normal component. ET, sorry, EN. Why did I put EN? I'm just rushing it. E-N, E-T. This is M-E-A-N-M-A-T. Just going to wait here, see everybody follows what I did. So immediately after cutting, this starts falling down. Right? It starts following a curvilinear path. Now that curvilinear path, well, it's motion on a curvilinear path. I can show that with tangent normal components. ET is tangent to the path, tangential to path. En is from the object towards the wherever the rotation is happening. Now I can still write this, right, is equal to MA. This becomes summation of forces in tangential direction, MAT. Summation of forces in normal direction is MAN. Now let's see what we have as AT and AN. I said immediately after. Right? So we have immediately after. Immediately after. We have acceleration. We don't have velocity. So I follow my whatever I said there, right? So if you write this, this becomes this TB is equal to, oh, let me write it this way, 2TB minus mg sine 45 degrees is equal to mr omega squared. And oh, I wrote it in normal direction. So let me follow the same tangent normal I wrote there. The first one, first I wrote tangent. So let's look at the tangent. Well, TB is in normal direction, so it's gone. We have mg is positive tangent direction. So that would be mg cosine 45 degrees. Remember, this is 45 degrees. This is 45 degrees. mg cosine 45 degrees. Nothing on free body diagram. On kinetic diagram, I get m r alpha. And normal direction, I'll get TB minus mg sine 45 degrees is equal to mr omega squared. Now, as I said, don't have velocity. So this becomes 0. Omega is 0. We have some value for alpha, right? We don't know. We can calculate that actually. It's not asked here. It's just we're asked to find the force TB right here. So if this is 0, this whole thing becomes 0. Right? From there, we can find the value for TB. TB becomes mg sine 45 degrees. Mg sine 45 degrees will give you 13.9 newtons. I went through this fast. So question on this one. So the trick was immediately after. Once you cut, it becomes a curvilinear motion. You have the path, tangent, normal path, a typical situation, like as if you have a mass there and you let it go suddenly. Since it's immediately after, you have acceleration, but acceleration did not have enough time to create velocity. Right? Conceptually, think about it. We give force to an object. That force causes acceleration. That acceleration causes velocity. That velocity causes displacement. So it goes in this order. Acceleration needs some time to cause velocity, to create velocity. Velocity needs some time to create displacement. Maybe you're talking about fraction of seconds, but it is still that's the order. All right.